Today I will be talking about my contribution called towards establishing a cooperation measure for coupled movement in close proximity human-robot interaction. This work is part of Socrates project funded by the European Commission. My name is Antonella and I work in human-robot interaction safety design at Bristol Robotics Laboratory based at UAE in the United Kingdom. In an aging population, the social and physical assistance for older adults is gathering more and more attention in the research community. One of the activities of the daily living which enables older adults to remain independent is that of dressing. This task is a physically assisted task because it requires close proximity interaction, but most importantly, continuous adaptation with respect to the user arm movement. The dressing task can be designed as an adaptation of learning by demonstration, which can allow the continuous adaptation of the human movement can be learned, predicted, and coupled with the robot's movement in order to do the appropriate adaptation. However, for safety interaction, the human movement skill in performing the task needs to be evaluated even when unexpected events occur during the interaction. The adaptation of the close proximity movements of the robot and the factor with respect to the human need to still be viable to maintain user safety. But also, it requires that the variations in the robot trajectory still lead to achieving the overall goal of getting dressed, or in some cases, abort the task for user safety. The aim of this human-robot interaction experiment was to capture how the human movement changes when unexpected events occur in the context of physically assisted tasks. The picture on the slide shows a timeline of one dressing task. The overall experiment layout was designed to try and evaluate what variations in an already learned skill of the human movement can occur due to unexpected events. The cognitive overloading and distractions in the environment directly disrupt the participants. The unexpected events were controlled to occur during the first half of the dressing sequence, in which the arm movement was not restricted by the jacket. The hypothesis behind the design of this experiment is that the human movement will vary, and this recording will allow us to learn what type of coupling and adaptation are adequate during unexpected events in close proximity interaction. The diagram here shows the overall experiment layout. In part 1, the participants were recorded performing the dressing task as shown in the previous slide for 10 times. In part 2, the same 10 dressing sequences were repeated, but this time a cognitive overloading was overlapped on the first half of the dressing sequence. In part 3, another 10 dressing sequences were repeated, with a distraction overlapping on only one of the dressing sequences. Cognitive overloading and distractions led to failures in the assistive task. Variations of the human movement learned can be used to quantify to what extent the user is cooperating during the assistive task. The potential of cooperation measure enables better coupling with the robot movement, while also allowing to assess the viability in achieving the task safely based on the current state. For these experiments, we are interested in whether or not the user's skill in collaboration changes when distractions and cognitive overloading occur in the physically assistive task. The human movement was recorded using an accent skew. For the coupling and cooperation measure, we focused into looking at the movement of the right human arm with respect to the robot's right hand effector. Statistical feature engineering were extracted from the dataset, and the approach of a sliding window on the time series was implemented. The evaluation of the cooperation measure needs to correlate with the high number of failures that occurred in part 2 of the experiment. These will be evaluated through the features extracted from the dataset and by finding a proper similarity or distance measure between the human movement distributions and features with respect to the robot's trajectory. This cooperation measure will allow to highlight changes in the human skill to perform the physically assisted task due to the unexpected event. Here, depict the relative entropy between the human arm movement distribution in the hand and elbow with respect to the robot's hand effector as a possible cooperation measure. This suggests that from the recorded movement, the participants in part 1 are managing to perform the dressing task in a particular synchronized way with the robot's movement. In part 2, the relative entropy suggests that the variance in the movement is much more bigger, which is an indication that cooperation is lacking due to cognitive overloading. In part 3, the relative entropy depicts the user performing the dressing skill in a more synchronized way with the robot's movement. Abandoning this information in an adaptation in any close proximity interaction allows us to have a true pulse on the type of cooperation the users are performing through their movements within the same skill. This measure will allow for safer interaction given the current state of the human movement and the progress in the task adaptation can be deemed if viable or not in order to avoid failure and to safeguard the human in the end.
Okay, if Antonella is available, I have two small questions. Antonella, are you in? If she's not here,
okay,
we can
move to the next video and we'll see.
Oh, 1 second. I just added her. It was a different name.
Ah, okay. So, but anyway, we can skip and then I can ask her the question. Is not a problem.
Oh, she's on now. You can ask.
Okay, Antonella, are you in? Maybe it's better to move to the next, to skip to the next one.
Hello,
So,
yes.
Antonella?
Yes, hello.
Okay, we just saw your presentation, very interesting. I have two small questions. The first one is related to the setup that you used. Which kind of sensor you used for the experiment? I saw the Ixen suit, so I think you were using the IMUS.
Yes.
And the second one is a different question, and is which is the best scenario for your experimental setup? If I got that you mentioned assistive robotics in general. If you can explain a little bit about this.
I think what we are trying to look at is when you have any type of cooperation measure and you try to learn what in an ideal situation the user is likely to cooperate and what types of movements they usually are going to implement. But in order to have an overall safety measure in your interaction, you also need to evaluate how that skill changes. If changes in the environment can affect the interaction between the person and the robot. So it's not just as simple as learning the interaction, but in unexpected events, such as we show distractions and cognitive overloading, can lead to the person to distract it away from the assistive task. And when you have at hand assistive tasks which are in close proximity, then it's dangerous, and you need to kind of create a measure of safety on which it assures you that the user is still cooperating just through movement. You can also do that through additional modalities, but we were interested in looking how you can extract these type of changes from the same primary skill just by looking at the movement. I don't know if that answers your question or not.
Yes, thanks. It's about the sensors.
The IMU, the Ixen suit was used, yeah. We didn't opt to use the open pose because you have some occlusions in the dressing, so it was an easier way of just using the Ixen suit just to get the movement extracted in a very nice way. So that's why we used that.
Okay, thanks a lot. Thanks. We can move to the next presenter. She is Sara Falcone, and the contribution is individual differences and the sense of the embodiment, looking for a correlation in an out-of-body experience.
I am Sara Falcone from the University of Twente, and today I present the preliminary work and the sense of embodiment in teleoperation tasks, particularly investigating if the proprioceptive information of an individual can affect the embodiment experience. In this presentation, I will give you an idea of the background. I will explain our research question, the experiment setup, and the tasks that we design. First of all, what is the sense of embodiment? It can be defined as the experience of perceiving another body or part of it as our own. This concept is applied to teleoperation, namely the control of a device or machine remotely. Indeed, it was demonstrating that a high sense of embodiment can improve the operator's task performance, since if the sense of embodiment is high and consistent, the operator's perception of the remote device as mediator is lower, and the teleoperation system is more transparent. In order to test the sense of embodiment, we have to consider its three components. The sense of ownership, defined as the feeling of self-attribution of an external object or device, which is easier if we consider a humanoid device such as a robotic hand, but it becomes harder with a device such as a drone. The sense of agency instead is characterized by the trust that the operators put in the fact that their intended actions are mirrored by the control device and the level of control that the operator has on the device itself. Finally, the sense of self-location is defined as the volume of space where one feels located. Ideally, in teleoperation, this space is the remote environment. As already said, we are interested in individual differences. Therefore, here we want to investigate if people with high level of proprioceptive information are more resistant to delusion, since they are more consciousness of their body parts and where they are located in the space. In the literature, the hypothesis that a higher level of proprioception brings to a lower level of sense of embodiment was presented but never tested. Moreover, always according to the literature, we decided to choose as target group dancers and gymnasts at a professional level, whose proprioceptive information level should be higher. We realized a between group design, and in order to assign participants to the target group, we first tested the proprioceptive level. As you can see from the picture, that was the setup. Two experimenters, one who provides the stimuli, and the other wearing the headset and the yellow glove. This second experimenter was wearing a headset as the participant, the one on his right wearing the blue glove. But the experimenter had, on the top of his headset, a stereo camera. The images were streamed in both the headset. Therefore, the participants were experiencing the first-person perspective of the experimenter for all the duration of the experiment. We designed three main tasks. The first is the cross-modal congruency task. It was based on congruent and uncongruent visuotactile stimuli, and there were two variations. In the first case, the participants saw a stick which touched them, but half of the times we did not touch the participants, but just the experimenter. In the second case, we touched the participants with three objects: the tip of a pen, a brush, and a soft ball. And we asked them to tell us which object we used. Again, sometimes the two were touched from the same object, and sometimes no. In the agency task, we asked the participant to link the dots on a drawing that they saw on a tablet. We asked to go from one target point to the other after our signal go. And remember that they could not see their hands, but the experimenter's hand. So they were sort of blindfolded. And we could measure the proprioceptive drift, measuring the distance between the target point and the reach point. And we could also observe their trajectory to reach the point. This is because they were accomplishing tasks using a drawing software. Do you remember the yellow glove that I mentioned before? Well, after the agency task, we asked the participant to tell us the color of the glove that they were wearing. What we expected was that if they were immersed in embodiment illusion, they would have answered yellow. Finally, in the last task, we used the surprise effect to break the illusion, and we pretended to stab the participant with a fake knife. During the experiment, we were also measuring the skin conductance response and so the level of stress. Indeed, concerning the measures, we used both qualitative and quantitative ones. For what concerns the qualitative measures, we collected the proprioceptive information of the participant through some information related to the age, gender, practice sport, at which level, and previous problems to nerves or muscles. We also conducted the questionnaire on the sense of ownership and agency. The qualitative data instead were represented by the proprioceptive drift, the reaction time, and the skin conductance response. Now it's time for questions. Thanks for your attention, and if you want more information or clarification, do not hesitate to contact me.
Thanks, Sara, for your contribution. Are you here?
Yes. Hi.
Hi. I have a question. Let's say it's not probably a question, but a curiosity. I was wondering if via your experiments, the experiments you shown, you were able somehow to answer to your research question of the dancers and gymnasts that are more resistant to illusions.
So this is a great question, and actually I would like to have the answer until now. The problem is that we managed to actually did just pilots of the experiment, and so we still don't have enough data because then there was the COVID and the lockdown. So yeah, it was really an unfortunate moment, I would say, yeah. And so unfortunately we still don't have enough data. And yeah, so that first research question, the one concerning really the dancers and people with normal level of proprioceptive information, I cannot really answer that. What I can say is that actually starting from this really preliminary study, the idea would be to do lots of more explorative study and collecting more information in order actually to try to arrive to this idea of being able to profiling people before actually put them in a context in which they have to deliberate and see if actually this information could help us in better understand and help them in the training part, and so reducing also the time for do that.
Thanks. It was just a curiosity.
I'm sorry. I would like to add the answer.
It's interesting to understand your journey.
Can I ask one quick question, very quick?
Yes,
So where did you put the skin conductance sensor?
On the palm of the hand, but not the hand which was receiving actually the stimuli, because that one had to be used and moved during the experiment, so there wouldn't be lots of noise on the other hand.
So
which was
this part or the inside?
No, the palm.
The palm. And did you had problems in that case with humidity or transpiration?
No, not really. No. This sort of problem, no. But again, it was really for 4 cases because they were all pilot studies. So maybe with, I don't know, 30 people, I would have had more problem. But for the cases that we did, we didn't have any kind of problems. And you have also to consider that actually during the experiment, they were wearing the gloves, but to both hands. And also if we were wearing hands, there were not this sort of problem. So.
Okay. Thanks.
Thanks, Sara.
Thank you.
So the next presenter is Natalie Friedman, and the presentation is on capturing attention with wind.
I'd like to tell you about our paper called Capturing Attention with Wind by Natalie Friedman, David Godeke, Vincent Zhang, Dimitri Rivkin, Michael Jenkins, Zidun Gautier, Arlene Stella-Chouliou, and myself, Greg Dudek. And this was work done at Samsung AI Center in Montreal. And the whole point of this paper is to find ways that robots can interact with human beings in socially acceptable ways, and in particular move through crowds where people might be in the way. Our key finding is that by using a novel haptic cue, that is blowing a little wind, we can get people's attention and move through a crowd. When a robot has to navigate through a scene with people in it, it's often the case that it has to approach a person who's blocking its way and induce that person to move. In this study, we look at how a robot can accomplish that task, for example, by blowing a little wind on the back of the person to attract their attention. We examined 3 different cues in this work: a visual text cue, an audio cue or sound, and a haptic cue in the form of wind. The idea is to allow the robot to navigate politely through people-filled spaces, and we show in the end that the success is removed by using the cues we want. We investigate 4 conditions: no modalities, wind with visual cues, and wind with visual and audio cues. And here you'll see a sense of what the experiment looks like, the track on the floor the robot has to stay on, and the nature of the cocktail party in which it interacts. And here's the tele operator's view. We're using Wizard of Oz control. This is what the operator sees as navigating the robot. Here's what it looks like when the robot uses no cue at all. It simply cannot make any progress at all through the environment. This is the motivating example. Here's an example of constructive engagement on the left, where one of the participants engages with the robot after noticing it. Here's an example of a successful trial where the robot is blocked by a bystander. It prompts them to gain their attention. They look at the cue on the screen, and then finally they move out of the way so that the robot can pass. Here's another successful engagement where the robot has to encounter a person and then induces them to move. You'll see that the Wizard of Oz operator has to work a little harder to get the robot to move past the person, even though the scenario is fairly simple. Here's another engagement with one of the same subject seen earlier, where the robot encounters them and they need to move out of the way. In this small social gathering, the robot sometimes encounters the same person more than once. In summary, more modalities are better, and combining haptic audio and visual cues is best of all. In summary, social navigation through crowds is tricky and requires the acquisition of attention. Using multiple modalities, including directed airflow, helps us do this and gives a richer perception of the robot itself.
Okay, thank you. Natalie, are you in?
I'm here. Hi, Claudia.
Hi. I would like to ask you one thing. If I got well from your for the presentation, you are using different modalities to capture the attention of the human, no? Video, so the visual, the audio one, but the wind, no? Yeah. So I was curious about the role of the haptic air cue with respect to the others. If you did somehow a comparison, doing experiments only with the haptic air cue or with the others separate, if you are able to identify the role of the wind in this research.
Right, so yeah, that's definitely a challenge because we didn't do just haptic by itself. But I guess this was just the pilot, so we were kind of figuring out, we were taking a design approach and iterating on different modalities at first to see if there was any difference in behavior of the people. And then it turns out that the haptic in combined with the visual and the audio cue did make a difference. So I think that to answer your question, like in the next study after the pilot, we would probably do just haptic and see if that makes a difference by itself. I guess also like in the context of a party, sometimes it gets loud and you won't hear the audio cue. And sometimes you're not you're not looking at the robot, so you don't see the visual cue. And the haptic is kind of serves to be a little tap on the shoulder.
Okay, so you replied to the next question about the importance of understanding the role of the haptic air only.
What did you say? Sorry.
I said that you already answered my question. The second question that was, do you think it's important for you, for your research, to consider only the wind, let's say? So yes, yes, thank you.
Actually, I had another question, which was, do people, is it just simply that you're trying to get their attention and I guess then they look at the cue, but I could imagine that if you play certain cues, such as like a car horn beeping, people might have an innate reaction or learned reaction to get out of the way, right? So could it also be with experience? Like, I don't know, maybe this is creepy, but I imagine like if someone came and like blew on me, you know, my reaction wouldn't be to get out of the way, it would be to be startled and to turn around and investigate more. Whereas if I heard a beep, I'd know like move.
Yeah, it was definitely a tricky thing. We wanted to think about what was as like socially appropriate as possible. So like at a party, a horn honking is like kind of strange. And also like a robot physically touching you is just a lot, like as you all know, is a harder robotics problem. It could also be dangerous, like you could poke someone too hard or that person could move into the robot by accident at the same time. So we saw haptic as like the fan as the safest, but it also is, questionably socially appropriate. But yeah, it's a good point. It's I guess also like this will be an iteration of like different modalities and different ways of expressing.
It could be a learned cue or something like that.
Exactly right. And then the thing is also like if this robot is at a new party every time and like different people every time, then like can it ever be learned? Like it also has to do with like the learning of the people.
Yeah.
And the experience of the people.
Thanks.
Thanks.
Thanks, Natalie. Okay, so we can go with the next one. He is Daniel Gonzales. So he's talking about passive gate synchronization of human-robot system using a dynamically coupled double rimless wheel model.
My name is Daniel Gonzalez, and I'm a postdoctoral fellow at the Robotics Research Center at West Point. I'm here to present work conducted with Professor Harry Asada at the Dyarbalof Laboratory at MIT. What had me curious was how a human and robot that are coupled together, like this guy you see here walking with the robotic backpack, how can they achieve steady locomotion using only passive physical connections? If you design this connection carefully, the human and the robot will naturally fall into a very special gait cycle. Let me tell you why we built this device in the first place. This is Jim Key, a nuclear nuclear decommissioning and cleanup contractor for the US Department of Energy. I was shocked to learn that the average age of these workers was around 50 years old. They'd frequently suffer from repetitive strain and other back injuries while wearing their heavy personal protective equipment. The limited air they carry on their back and the potential for heat fatigue in their hot and humid work environments limit the amount of time that they can stay at a task location. Being able to carry a cooling system and some extra air with them would make their job much easier, but it would be too heavy without some kind of augmentation. This is why we built the extra robotic leg system. It's essentially a backpack with a pair of articulated robotic legs that walks with the human operator while bearing the equipment payload. But in order to achieve stable walking with the human operator, the locomotion strategy should return to a desired footstep pattern when perturbed. This is difficult, however, because the robot cannot control the human directly, and vice versa. But we can get these two halves to synchronize naturally, without control, using a very special gait cycle found in nature. In this gait cycle, the rear leg footfalls lead the front leg footfalls in such a way that the front and rear halves are synchronized, but 25% out of phase. Of the 6 possible 4-beat footfall patterns achievable by quadrupeds, this gait cycle maximizes the center of mass margin from the edge of the support polygon. 4-beat walking exhibits minimum energy losses, leading to the fastest steady-state passive walking speeds. What is perhaps most intriguing about this gait cycle is that the front and rear halves of a quadruped exhibit the same energetics as 2 bipeds walking 25% out of phase. If the human XRL system can be designed to passively synchronize to this special gait cycle, we can supplement this already natural stability with feedback control to achieve additional robustness. To understand our dynamic model for this 2 biped system, we must first understand the canonical rimless wheel. This passive model captures the natural dynamics of bipedal walking using only gravity to inject energy into the system. It's essentially an inverted pendulum on a sloped surface. We provide a constant angle of forward lean when the wheel takes a step with the other foot. The landing foot becomes the new pivot point, only angular momentum about this new point is conserved. The remaining momentum is sufficient to vault the pendulum over and continue the walking cycle. What we did was take 2 of these rimless wheels and connect them with a spring and damper to get the dynamically coupled rimless wheels model. Each one still triggers its hybrid reset independently, but the mass centers influence each other through the dynamic coupling. Including the dynamic coupler gives us 3 nonlinear state-determined dynamic equations of motion, which can be simulated using an ODE solver. If the spring and damper parameters are chosen correctly, the wheels speed up and eventually synchronize to the desired phase difference. We can see a trend here when the front wheel takes each step. The rear wheel angle, θ2, converges to 0. Using guidelines from our paper, we can select for physically realizable coupler components. So if we rerun the previous simulation with these values based on hardware components, we find that it converges within 20 seconds. This simulation forms the basis of our physical model. A physical, coupled pair of rimless wheels was fabricated to achieve a human-like step length of 15 degrees and a leg length of almost 1 meter, just like the simulation. The wheels were sent down a gentle slope with an initial out-of-phase condition. By tracking phi, the difference between θ1 and θ2, convergence can be observed in under 10 steps. The physical system converges faster than the simulation, which we hypothesize is because of unmodeled elastic impacts. The same convergence can also be seen in the second experimental trial with different initial conditions. This passive method of gait synchronization, combined with a well-designed control system, shows promise as a means of enabling the human XRL system to achieve stable locomotion. And with that, if you have any questions, please do not hesitate to contact me.
Daniel is available. I have one question.
Yes.
Okay. Daniel, how much your system is robust to variation of motion directions? I mean, I saw the cat, but if I start walking as a crab, does it work, the system?
If you start walking sideways, we haven't checked any lateral motions yet. We haven't designed that in just yet. but I'm sure if you instrument the legs as we're planning to do on the ankles, you can actually then kind of synchronize in that form in order to really make sure that your balance is okay, right? That if you're slowly walking sideways, or if you're even shuffling very quickly the way you would, you know, for football training or something while wearing this thing, I'm sure that a
So you have
controller
to
that, excuse me?
No, I'm saying you have to redesign the model a little bit, to change the model a little bit, of course,
So it would
because
be a different model.
yes,
right?
probably
Yeah.
a
It would be a
redesign.
different model that would be designed in order to handle the left and right synchronization,
Okay.
right? The lateral synchronization.
I have a question for Daniel, if I can. Claudia? Yeah.
Yes, of course.
Okay.
Yes.
So, was there any reason you didn't use wheels instead of feet? So in your design, would it be easier, maybe?
Oh, absolutely. Depending on where you're operating. So one big requirement for the design of this thing was it had to climb upstairs, and it had to deal with very unstructured environments that were not really designed for purely wheeled motion on carts. In fact, the workers, what they tried to use, they tried to take everything that they would wear on their back and put it on a cart beside them and have a hose connected to it. But they didn't like that because, one, it was difficult for the wheels on the cart to actually go around and get around all the obstacles, climb up the ladders and anything that they had to navigate around. And they had to really be careful about disconnecting the hose, right?
Okay.
In those environments, the particles that are radioactive are in the air. So the risk is not exposure just through rays, but it's actually breathing in particulates that would then, you know, give them cancer, not give them a good time. So for that, we really wanted to focus on walking specifically.
Okay. Thanks.
Thanks, Daniel, again. The last presenter is Dojin Park with Trust Learning for Initiating Physical Human-Robot Interaction.
I'm here in 1 second. I'm just having trouble with the very last presentation. In the meantime, I think we have one question for Danielle while I'm just solving the issue.
Was that the question that was in the Q&A about is the load?
Yes.
Okay. So the question is the load, I'm guessing the load of the backpack, right, of your payload, is that all borne by the XRL system, or is part of it shared by the human? The point of it was to really make the human feel as if they're wearing nothing at all. So a lot of supernumerary limbs that came out of Professor Sada's lab in the past had legs that were attached but were free to move around independently and were not tied to the ground at all. What this system in particular was designed to accomplish was bearing all of its own load and all of the payload. So it was designed with that in mind.
Okay, thanks. I think Claudia, you can take over if you can see my screen.
Yes, I can see the screen. Yes, you can launch the presentation.
Hello, my name is Juyoun Park, and I'm a postdoctoral researcher working with Professor Dojin Park at the George Washington University. I'm going to talk about our research, Trust Learning for Initiating Physical Human-Robot Interaction. I will give you a brief introduction and explain our methodology, pHRI-based simulation, and trust learning. Then I will show you our demonstration video and conclude with discussions. In some situations where contact between people can be dangerous, like these days, robots can effectively reduce the risk. Physical human-robot interactions can provide alternative solutions in conducting basic medical tasks, such as temperature measurements, while reducing physical contact between people. In physical human-robot interaction, trust is one of the essential factors. To learn the police getting closer while gaining trust, Responses from the person should be recognized and applied to police learning. However, there are challenging issues in the real-world experiments. Therefore, we propose a hybrid simulation that a simulated robot runs the police based on real-world human responses. In the proposed simulation, a human in the real world participates in the experiment as an observer, and intention is reflected during the simulation. We applied reinforcement learning to process those features and train the police. We implemented a simulation environment based on Quiblet and used the humanoid robot Pepper. As you can see in the figure, there are Pepper and the human model in the environment. A user can watch and participate in the simulation in real time. For each episode, the question box is popped up and the user can answer by clicking yes or no. During the simulation, facial part is detected from the RGB images, and facial features related to emotion are extracted from the convolutional neural network. The extracted facial features and the distance values obtained from the 3 laser sensors on Pepper become states and used as inputs to the trust police network. Based on the output action from the police network, Pepper moves. Reward is calculated based on action, distances from laser sensors, and users' answer. The police network is trained based on reinforcement learning. The goal of the simulation was defined as the distance between Pepper and the human model would be 50 centimeters. The states were defined as the extracted facial features and the laser sensor value. The actions can be selected on the 5, Pepper moving forward, moving backward, moving right, moving left, or stop. The reward was defined in these 4 ways. Here we applied augmented actor clearing method to train our police network. This reward graph was resulted from our demonstrations, and you can see the reward increased over the first 300 episodes and converged. The increasing rewards verified that our simulation and police network were effectively applied so that Pepper can get closer while make the user feel comfortable. The proposed simulation environment is displayed here, and I will show you 3 selected episodes from our demonstration video. Our proposed hybrid simulation reduces the issues occurred in the real-world pHRI experiments, and we can train the police network safely. We expect our trust police learning can be used in various situations involving physical interactions. For our future work, we plan to add dialogue interactions based on natural language processing, and we also plan to use this simulation to learn the police in real pHRI situations. Thank you for listening.
Okay, Juyoun, are you in? Hi. If I got well, your approach is it will used for assistive robotics, no? But do you have in mind any specific application of this?
Actually, we target this approach to develop robot for assisting medical employees these days, because in this situation, there are much dangerous situations that medical staff are in dangerous, they should measure temperature body temperature or give diagnosis on some possible patients in these days. And in this situation, they are in danger. They can get some disease through that diagnosis procedure. So we purpose to develop robot platform to do that diagnosis instead of medical staff. So we will apply this approach to develop a global platform that can do some basic medical diagnosis.
Okay, thanks, very clear. So I would say that this is the end of this part.